So today we're going to start Chapter 2. Chapter 2 is going to move into a discussion of functions. 2.1 specifically, we're going to talk about what a function actually is to start with. So a function is simply a rule that assigns each element in one set to a unique element in a second set. The input is your first set. The output is the second set. And then when you see independent and dependent variables, they correspond to the input and the output as well. So the independent variable is the input. It's also called the domain. And most of the time we use the variable x. That's kind of our default. The dependent variable, because it depends on what the input is our output. It's called the range. And typically, it's either called y, or we're going to have a new notation that looks like this. Has an f, has a parenthesis, x, close parenthesis, and it does not mean multiplying f and x together. Parentheses is probably the biggest frustration to try to clarify what they mean, because they mean many different things. You identify points by putting parentheses around them. We did interval notation in 1.7 where we put parentheses around things, right? And here, we use parentheses to indicate multiplication. And here we use parentheses to indicate that the output is f when the input is x. That's what it's indicating. So it's telling you the output is the function, and it's also telling you that it's a function itself as well by having it written that way. Parentheses are very confusing. So we're going to do an example. Suppose C is the cost of mailing a letter, and W is the letter's weight. So even as I say this, I realize that some of you may never have mailed a letter before. It's kind of an old school thing to do. But maybe you've mailed a bill off to something where you did actually send money in that way, or maybe you've mailed something back for a survey you've completed or something like that. So we're mailing something. C is a function of W. W is a function of C, both or neither. It's asking which of those things happens. So I want you to imagine two different things. We'll first start with the question of whether or not your cost, and it's cost and weight, right? So when you take the letter in, and let's say that Tori has a letter that has one piece of paper inside, okay? So it's got one weight, right? One weight, one piece of paper. And Aspen takes hers in, and hers has two pieces of paper inside. Maybe it's a piece of paper and a check, like for a bill you're sending off or whatever. So yours is a little bit heavier, but not a lot. I mean, they're close. Will the cost be the same, or will the cost be different for your letters? Will it? Has anybody experienced taking a letter into the post office before? So if the weights are very different, the cost is different. But if the weights are close, the costs are the same. So when Tori takes her paper in, and she just has one piece of paper in the envelope, the basic envelope, and you have the same thing, one piece of paper, basic envelope, and a check, yours is going to weigh a tiniest bit up more, tiniest bit. But the cost is still going to be one stamp, whatever the cost of one stamp is. I think it's 55 cents these days. I think I was told that recently. So your cost is going to be the same. So the weights were different, but the cost is the same. Does that make sense? And this is actually talking about specifically if you wanted the same type of postage, right? Just a regular, send it regular first-class mail, all right? So when we're thinking about this, we have to think about the direction of these things. So the first issue is to consider different weights. That's the one I did first. I did it differently in my notes, but that's okay. Different weights. So what that means is if you know going in that the cost is going to be one stamp, whatever the cost of one stamp is when somebody's listening to this video later on. Today it's 55 cents. Cost is one stamp, 55 cents. It means I don't know how heavy the letter was. Not exactly, right? Because I could have had Tori's letter, which maybe weighs like half an ounce, And I could have Aspen's letter, and hers actually weighs like 0.62 ounces, right? A little bit more than half an ounce. So the cost does not tell me how much the letter weighs. Do you agree? It doesn't. The cost simply doesn't do that. So if we have different weights, when we're looking at this, is the weight a function of cost? The answer is no. And the reason is because one cost, namely one stamp is how we thought about it, can have two really or infinitely many or more weights. Now, the way postage actually works is there's a limit to that, right? There's only so many things I can continue to add inside that letter before it does bump to the next postage stamp cost, and then you have to pay an additional ounce price. But as long as it's under 1 ounce, that's actually their number, it's the same price, whether it's super light or whether it's like 0.97 ounces, like right almost at 1, all the same price. So the weight is not a function of the cost because you cannot tell me the cost, and I can for sure tell you how much the letter weighed. Let's go over here to the cost as a function of weight. So the second issue with letters being mailed is that there are different ways to mail the letter. Are you sending it first class? If you're doing something that's an actual book, you can send things called media mail. It actually makes your book costs cheaper if you sell, like if you end up selling a textbook at some point or whatever. Definitely look into media mail; it's cheaper. Are you sending it FedEx? Is it UPS? Is it the post office that's sending it? Right? You can send a letter in any one of those ways. Are you sending it locally, or are you sending it to, like Europe? It matters. So your individual envelope, if you both took in an envelope and they were exactly the same weight, right? So that's not an issue anymore. We're not talking about the weight changing. We're trying to keep things only changing one variable at a time, one piece of information at a time. Your letter cost is not necessarily going to be a specific amount because it depends on other things, right? Do you want it overnighted? That's another one. You overnight something and it's going to cost you a lot more. So, is the cost a function of the weight? And the answer is no, because it can be different based on how it's mailed. And I'm going to say how/where, because where is an option as well. How or where it's mailed. So it is not, cost is not a function of W because of that issue. So neither of them worked, which means the answer for this one is actually neither. Now, if you took this question and you adjusted a few parameters, right, you changed a few things, and instead you talked about mailing the letter first class domestic, right, then it actually would work over here on the cost for the weight. First class domestic, because first class tells you exactly how it's being mailed. You don't have that flexibility to send it overnight, or UPS. First class, that's a UPS mailing distinction. Domestic, it's within the continental United States, Alaska and Hawaii, right? So we've got the US that we're sending it to. It's not going to another country. So since it's not going to another country, there's no variation there with the how or where it's being mailed to. So if we add a couple of conditions inside of the question, this could have the second one, that is the one I did second, not the second one unlisted, but the C is a function of W. It could work. Because if you had those conditions met the same, and Aspen took hers in and you mailed it to Wyoming, and Tori took hers in, they weigh the same amount, right? So we're not varying that. But Tori takes hers in and she mails it to Florida. They're the same weight. That's going to cost exactly the same amount because they're mailing it inside the United States and they're mailing it at a specific first-class rate. So if you add a couple conditions, this one could work. But these are the kinds of things that you have to take a look at as you're looking at whether functions exist. Do I know for sure it determines a specific thing? The vertical line test is often one of those pieces that we tend to remember. I think a lot of graphical things we tend to remember. The vertical line test talks about a graph representing a function, and it does so if and only if no vertical line is able to intersect the graph in more than one point. So I'm going to draw 3 different images. Sometimes it's hard to get my images to draw inside of PowerPoint, so I'm just going to sketch them. You would have actually been given these in the problem themselves if I could get the program to work nicer. It would look like that, and the last one looks like this. Okay, so these are the 3 that we're going to work with. The question is, do they represent a function, i.e., do they pass the vertical line test? So here's what the vertical line test says. It says that if I draw vertical lines, okay, I don't know what I just did. Let's move back to the next slide. I think I just switched slides accidentally. If I draw vertical lines, I'm asking myself, is it crossing the graph once or more than once? If it doesn't cross the graph at all, it's an irrelevant line. I don't care about it. I just want to know, is it crossing it once or more than once? And all of the lines I draw on the first graph cross it once. And when that happens, that all my vertical lines cross the graph only once, I have a function. It is, in fact, a function. But you'll notice if I draw vertical lines on the next one, what happens? Twice. Now there's the corners, like the edges, where I would only cross it once, right? I mean, there are some places potentially that I only cross it once. That's not a big deal. The issue is, do I ever cross it more than once? And the answer is, yes, I do. And so when that happens, it is not a function. Because in at least one place, all it takes is one place where a vertical line does it. Here, there's plenty, right? Lots of places. If a vertical line will cross it twice or more than twice, it's not a function. How about the last one? It is not a function. So there's plenty of options that I can draw. If my graph continued, I didn't draw it out very far, but you can imagine, right? It's going to cross it more than once in lots of places. Again, it has some places where it would cross it once, but those are sort of irrelevant because it fails at all the points, so it doesn't matter if it succeeds occasionally. This would also be not a function. And if you want to look back at the definition, I would like for you to consider why this is true. Like, I can think about this visually, and that's a great imagery, but why does it work? Well, because what a function is supposed to do is it's supposed to take an x value and tell you exactly what the output should be, guaranteed. The problem on these last 2 graphs is that if I take, say, I'll use green, this x value over here, right? Then on the graph, I'm here and I'm here. And instead of having just one y value at that x value, I have more than one, namely 2. Right? Instead of having one weight of the letter, I had 2 or more weights of a letter that all cost the same thing. Instead of having one postage rate for that letter, I had 2 or more postage rates for that same thing. That's why this one fails. But on the first graph, it doesn't do that. Every x value, so let's say I use this x value, has exactly only one point that corresponds, which means that if I know the x value, right, where the line is crossing, I exactly know the y value. There's no question. There is one y value associated with that x value. And that's what a function is. One output for every input. Now, if I have a general collection of ordered pairs of points specifically, it's called a relation. So a relation is just a collection of points. Okay, that's all a relation is. These would all be graphs of relations. They're not all graphs of functions, because the last 2 are not functions, but they are graphs of relations, because they're graphs of points, ordered pairs, right? That's what they are. So a relation is simply a set of ordered pairs. If I want to determine if a set is a function, I have to decide if every x value has a unique y value. So I'm going to just go down the list of this one, and then I'll show you a visual for how you can think about this too. Here's an x value of 1. Its y value is 7. Do I have any other places where it says x is 1 and y is something else? No. And I'll just go to the next one. X is 0. When x is 0, y is 7. Do I have any other places that tell me x is 0? No. So x is 0 makes that y is always 7. The next one, x is 4, means that y is 6. Do I have any other x is 4s? No. So y is always the 6 when the x is 4. And of course the last one works by default because there's nothing else to check it against. So every x value here has a unique y value. I know some of those y values duplicated. That's not a problem. The issue is, do the x's duplicate? Okay? So this is a function, if I think about it from that perspective, or at least one of the perspectives is to go sort of down the line. Another way you can do this is you can put them in kind of some groups. So these are my x values, and I'm just going to put them in a circle, and these are my y values, and I'm going to put all of them in the circle. So my x values are 1, 0, 4, and 9, and my y values are 7 and 6. Okay? And I'm just going to draw an arrow showing where it gets sort of sent. The x value of 1 gets sent to I think it was 7, yeah, the y value of 7, right? If x is 1, I know y goes to 7. If x is 0, y happens to also be 7. Again, that's not a problem. What I don't want is I don't want this 1 going to 2 locations over here, okay? And I don't have that happening on this one. The 4 and the 9 both go to the 6 as well. Again, not a problem. What I don't want is I want the 4 or the 9 actually going to 2 locations in the y range, the y values. So that's another image that you can think of from that perspective. If you'll notice, my second set of numbers is really just, I reversed them all. I just use the same numbers because there's nothing wrong with them. And I run into problems very quickly because this x value of 7 has a corresponding y value of 1 and a y value of 0. Right? The same x value, 7, different y values. That's the problem. And the other one fails too, but it really doesn't matter. If one place fails, the whole thing fails. This is not a function. If you like the imagery that I did before, we can do this here as well. I have 7 and 6 as my x values. And I have 0, 1, 4, and 9 as my y values. And the problem as you make your correspondences is that 7 goes to 0 and it goes to 1, and that's exactly what can't happen. I cannot assign an x value to 2 y values. Okay? So let me do, I didn't think to do it before, and I think it might be helpful to use a real-life example where I can show you a function versus not a function relationship. I'm going to flip back just so I have it on the screen where I had my my example here, because I gave you something that didn't actually have function status. Let's consider a domain, whoops, I'm going to use white, right, the x values to be, I'll just say kids, and I'm going to consider my range to be, my range y, to be, and I'll be very specific so that we make sure that this cleanly makes sense, and I'm going to say a biological mom. Okay? Biological mom. So we're not talking adoptive, we're not talking step, we're not talking anything, just biological mom for the moment. So if you consider this way, and you take a kid, every kid has exactly one biological mother. Agreed? They do, right? It's biology. God did it, not me. Like, that's biology. This is a function. But if I switch my x's and y's, it doesn't work that way. So if my domain x is actually all the bio mothers, right, bio moms, and y is all the kids, you cannot say that every individual biological mother has exactly only one kid, right? In fact, I don't know the percentages, but it's probably most that don't. I mean, only children are sort of the exception, not the norm, at least in our society. So this one would be not a function. So the order on this one matters Sometimes it is a function, right? One direction, I should say, it is a function, and the other direction, it's not. So that's actually an actual, like, real-life example of how functioning works. So we're going to do the same thing on this one, or we're going to do something new, on this one. We're going to take a look at the domain and range. Now, I've used that phrase, domain and range, back on that example that I just gave you with the moms and the kids. But what we're going to do now is we're going to look at it with like graph context, equation context. Okay, that's what we're going to look at it from these three examples. So we're going to find the domain and the range. And remember, the domain is the x values, and the range are the y values. And the first one that it wants us to go back to is 2a, which was a graph. So we're going to look at a graph on the first one. So this graph right here, right, is what we're considering, ignoring the yellow lines. So let's actually clean it up so it's easier to look at. Oh, I didn't mean to do that. I forgot. It's not on there. Like that. All right, so let me talk to you about, from a graphical perspective, how to think about domain and range. Because there's a really cool visual that you can use that it's quite helpful. So domain is supposed to be all the x values, and you know the x-axis is this one, right? So that's the x-axis. So what I want to imagine is I want to imagine that you're walking along the x-axis, just from the left to the right, okay? You're walking along, you're looking up and you're looking down, and you're looking up and you're looking down. You're in the domain as long as every time you look up and down, you see part of the graph, right? Directly above you or directly below you, or you're on it, right? If you're crossing it, that's fine too. On this graph, the entire time from the far left to the far right, you see parts of the graph as you're walking along the x-axis. Agreed? So on this one, my domain, which I'll just abbreviate with a D, is the entire thing. It's negative infinity to infinity. Starts at the far left, negative infinity, continues to the far right, positive infinity. And I'm walking along the x-axis. So if the domain is walking along the x-axis because the domain is x values, what do you suppose I'm going to do for my range? Same thing, but with the y-axis, right? So I don't think I can really walk along the y-axis, but I could climb. So imagine that you're climbing up the y-axis. You're starting at the bottom, it's like a ladder, and you're climbing up. As you climb up, like this, instead of looking up and down, because that doesn't make sense, you're going up and down, right? Instead of going up and down looking, you're going to be looking left and right. So you're climbing and you're looking left and the right. And everywhere you see to the left or to the right, part of the graph, you're in the range. And if you take a look on this one, every time you're going up on this one, you always see part of the graph to the left or to the right. There's no gaps, there's no breaks. So, for this one as well, the range is negative infinity to infinity. You see parts of the graph everywhere. So that's how you can think about it from a graphical perspective. The second one talks about looking at it from a points perspective. So it's example number 6. Hang on, I'm on 6. Example number 3. Take that back. This one was a function. The domain is supposed to be all the x values, and the range is all the y values, and this is the easiest type to do because all you have to do is list them. It's just a bunch of numbers, right? What numbers are the x values? Well, I actually drew them. They're right there. Yeah? Those are my x values, and here are my y values. So when I'm doing my domain and range on this one, I'm just listing values. And the way that I notate it is I actually put it in curly braces because they're individual points. So they are the values. I'll put them in order, not because you have to, but just because I can. 0, 1, 4, and 9. That should say domain, sorry. The next one will say range. Okay, so my domain is just the list of the x-coordinate values that are in that list of points. And my range would be what? 6 and 7, or 7 and 6, either way, yeah. The order doesn't matter. That's my range. So when you have a list of ordered pairs, I think that's the easiest one. Honestly, though, sometimes people get confused because it feels like the one we do the least. You don't have as much practice with it, but it's definitely straightforward, simple. 7 is the most difficult because it's an equation. I mean, truthfully. So there's a couple of different things you could do. You're welcome to look at a calculator to see what this graph looks like and to try to do it from a graph perspective. I have no problem with that. Okay, I'll draw that one here in a second. But you can also do it from an algebraic standpoint, from an equation standpoint, using what you see here. I'm actually going to start with the range because it's easier to see than the domain. The range is what comes out of a square root function in this case, because I've got a square root. So what kind of numbers come out of square roots? Positives, right? Do zeros come out of square roots? Is there a square root of something that gives you 0? There is. The square root of 0 is 0. So it works. It's kind of by default. Do negatives come out of square roots? Not if it doesn't have a negative in front of it, right? And this one does not. Right? There's no plus or minus in front of this. So there's no negatives that come out of this. So what happens is I only get positive values coming out of square root functions or 0. So my range is going to be either, you can write it in interval or in a set notation like we've seen before, is x, it's not x, it's y. Y is greater than or equal to 0. You can write that. That's fine. Or you could indicate it using interval notation, which means 0 to infinity. Again, I'll show you a graph on this one too if you like the graphical one better in a sec.
Why would there be a graph?
Because you can equal 0. The square root of 0 is 0, which means I can get a 0 to come out of the square root. Yes. If I couldn't, like if this had been the same thing but in the denominator, so I can't have a 0 in the denominator, I'd put a parenthesis on it. And you might have an example of that one in your homework, I think, actually. Domain means what am I allowed to have inside of the function. What can x be? Well, x can't be just anything. There are numbers here that don't work inside of radicals, at least in the real number system, right? Back in section P7, we talked about what happens when we have negatives underneath radicals. Do you remember that? We've got imaginary units. We're not working in the imaginary plane right now. We are working with real numbers only. So I can't have negatives underneath my radicals in this world that I'm working with coordinate planes and so forth. So I need this piece that's underneath here to be greater than or equal to 0. I can't have negatives. And what happens right here then is I have an inequality that we just talked in section 1.7 about how to solve. What will you do first? Move the 5. So negative x is greater than or equal to negative 5. And then divide by negative 1. I change the direction of the sign, so now it's less than or equal to. And negative 5 divided by negative 1 would be 5. Right? So over here, my domain, if I want to use set notation, is that x is less than or equal to 5. If you were looking in the back or you wanted to use interval notation, that's telling you you need numbers that look like this. Negative infinity to 5. So just think for a moment about what would happen if you had something bigger than 5. Let's just use 6. 5 minus 6 is negative 1, right? That's why I can't have them. It's because that gives me a negative underneath there. But if the number is smaller than 5, like 4, 5 minus 4 is positive 1, and I'm good to go. I end up with positives underneath there. Let's look at a graph of this just so that you can see, and if you don't have a graphing calculator, then this is irrelevant to you. But if you do have a graphing calculator, let me show you what we'd see, roughly speaking, if you looked at it. So you would put this equation into y1, or into the graph if you have a different kind of calculator. And your graph, I'm going to do it because I don't want to draw it wrong. I don't have it drawn on my paper. The graph looks like this. Roughly. It actually stops right here. If you trace along, you can figure out what you're seeing and at this specific point. This specific point is actually, you're hitting the axis and you're at 5. And that's what's happening here. So if we think about this from a graphical perspective and we're walking along the x-axis for the domain, we start from the far left, and as we move to the far right, we have values clear until we get to 5. And at 5 and beyond, there are no y values beyond 5, or x values, no graph. If I look up and down, there's no graph beyond x equals 5. So that's why my domain is going from negative infinity to 5 and it stops. On my range, if I'm climbing up the y-axis for a really long time, right, the entire bottom half of the graph, I don't have any values. There's no graph. I climb, I look left and right, I see nothing. Left and right, I see nothing. Once I actually hit the x-axis, which is y equals 0, and as I continue to climb up, I always see values. Now, they're increasing very slowly over here, by the way, but they still increase indefinitely forever. So no matter how far up I climb, I will have a location where I see a value. In this case, it would be over to the left-hand side. So that's infinity, 0 to infinity on the range. Okay, there's one more thing we're going to take a look at really quick today. It's really easy. It's called function notation, and we're just going to do it for a few examples. I think these two, and then we're done. The point of having function notation is because we can see what the output is, g, and the input is x. Input x, output g. So the reason that that's nice is because when I see something with like a 2 like this one on the inside, it's telling me that I replace the input x with the input 2. It's a replacement statement without having to use any language, is what it really is. So over here, what I have is I replace my x with the number 2. So it's 2 squared, and 2 squared is 4. We need to be very careful as we do replacements, though. The replacement needs to replace the entire value x. And the easiest way to keep track of signs in particular is parentheses. So this one actually says that x is being replaced by negative 2. So I'm going to put negative 2 inside a parenthesis because the entire x value, namely negative 2, is now being squared. So when I take negative 2 and I square it, I get 4 again. So what I don't want you to do is I don't want you to write it like this, because then you have to decide, where is that negative supposed to be again? Does the negative get squared? Does this become positive or does this stay negative? Right? Because that notation actually means it should stay negative. So we don't want to use that notation. We want to make sure that whatever we're inputting in for x has parentheses around it. Doesn't matter what the function is. So now my function output is 3x squared minus x, and my variable is x. So f of 2 means that no matter how many x's there are, they will all be replaced by the number 2. So I have 3 times 2 squared minus 2. And you notice the parentheses are around the 2's every input there is. And then we simplify. Order of operations always. So 2 squared is 4 times 3 is 12. And then 12 minus 2 would be 10. And there's nothing special about 2's and negative 2's, although I've used them. We could do it for anything, including another letter. So this other letter is W. I mean, okay, we just take all the x's out and we put w's in instead. I don't really know that I need parentheses for that, but if you want to put them, you certainly could. Right? It's the same thing as having 3w squared minus w. There's nothing I can combine. There's nothing I can simplify. I just exchanged x's for w's. And that might feel a little bit silly, but that's going to lead into what we need to do to finish this section out, which we will do next time. Have a great couple days, and I'll see you guys on Thursday.